last week we went through the electromagnetic spectrum. Okay, I described it, what the electromagnetic spectrum is, how at one end of the electromagnetic spectrum we have power, telephone, radio, radar, all the way down to from microwave down to infrared, and then the visible light spectrum. So a small section of this electromagnetic spectrum is the visible light spectrum. Okay, and beyond that we then start to get high energy including UV, X-rays and gamma rays. So gamma rays is the highest energy. Now, electromagnetic waves comes with energy. Light is energy. Light produces photons that allow us to see things. Microwaves can vibrate atoms that cause them to bounce against each other and creates heat. High energy gamma rays are so energetic that they can actually remove electrons. Okay, so in other words, they are ionizing. Okay, so let's now talk about this energy, the electromagnetic radiation energy. So energy is the momentum of the wave multiplied by the speed of light. Okay, so how do we know this? We know this from multitudes of experiments. Okay, that's how we know this to be true. Now, so energy is momentum times the speed of light. So E equals PC. Okay, and momentum, we know momentum from just basic physics is equal to mv. Mass times velocity gives us momentum. Okay? Now, in terms of electromagnetic radiation, we know that the velocity is the speed of light. So we're talking about a vacuum, of course. Okay? So therefore, momentum is also the mass times the speed of light. All right, let's have a look at it. If energy is momentum times the speed of light, then here we have momentum over there times the speed of light. So therefore, energy is the mass times the square of the speed of light. And this is where Einstein's equation, famous equation, E equals mc squared comes from. It is entirely proved. Okay? It's shown to be correct by experiment. All right? And as you can see, it's actually a very, very simple formula, easily derived. Now, so let's have a look at the wave formula in terms of energy. Energy is Planck's constant. So we know that Planck's constant times the frequency of the wave. Okay, so let's have a look at some of these. We've got energy is in joules, Planck's constant, and then frequency is in hertz. Okay, all right. We don't really care about the units for Planck's constant because it is a constant. Okay, I'll give you some exercises now to do, and then and we'll see how you go. If you have any questions, you can ask me. Have you got any questions about this right now?
What's Planck's constant?
Okay, so Planck's constant is derived from experimental data. Okay, with regards to waves. So what happens is waves will work differently, and then we can, if you like, average them out, these differences, and this is called Planck's constant. Okay? All right, good question. Any other questions? All right, okay, thanks. I'll get back to you.